Hello, I'm Jason and welcome to this section of the Chemistry Tutor. In this section we're going to talk about electrical properties of aqueous solutions. So before we get into that, I'd like to just take 2 minutes to kind of recap everything we've learned in chemistry and also encourage you that if these topics don't seem familiar to you or if you don't feel like you're really good at them, then stop now, go back to my previous DVD courses in chemistry and review yourself, because chemistry is kind of unique in the sciences. If you really don't get something early on, you will not understand this material now. It'll just seem harder than it is. All of this stuff is not hard, but you do have to master the topics leading up to it, otherwise you become lost. So more or less what we've covered up till now in chemistry is the essential bedrock. We've talked about the periodic table, which is basically a listing of elements that we know can now combine and form molecules, and we talked about the difference between molecules, molecular bonds, and ionic bonds, and how those things are different and how they're unique from one another. We've talked about how to name compounds. If you have magnesium and chlorine and they come together, how do you name the resulting compound? What do we think the chemical formula is going to look like? We've learned how to take the periodic table and figure out what charges the different elements are going to want to take so that when they combine we can predict their chemical formula. And then finally we talked at great length about what happens when we have a chemical reaction where we have two or more compounds and they come together and the chemistry happens and then spits some different products out the other end. And we specifically learned how to balance those chemical reactions for conservation of mass on the left-hand side and the right-hand side of the chemical equation. And we've learned how to use those stoichiometric coefficients, those numbers in front of the compounds, to basically do calculations with chemistry to predict how much of something is going to be produced or how much of something is required for a reaction to go ahead and go to completion, and so on. We've talked about limiting reactants, when you run out of one of the reactants first so the reaction stops. And then finally we talked quite a bit about solutions and molarity and the concentration of reactants. And what happens if you have things that are mixed together in solution and you have certain concentration of one reactant and a certain concentration of another reactant? How do you calculate then what's going to be produced? So that's kind of like a 2-minute thumbnail of everything we've learned in chemistry up to this point. And I just said that here in just a couple sentences, right? But the thing is that if anything I said in there sounds foreign to you or is like, well, I don't think I quite remember the molarity part, then you really need to stop now and go back and make sure it's fresh in your mind. If I'm talking about stoichiometry and limiting reactants and how we calculated the products, if that's something that you didn't ever quite get the first time, you need to stop now and go back and nail it. Because let me tell you, all of those topics, all of those concepts are going to be used from here throughout this section, the next section, the one after. So you're just going to slow yourself down if you're not familiar with it. So take a moment and make sure that you're familiar with that. Now, one final thing I'll say, as you watch these sections here in chemistry, if there's something you don't understand, if there's something that you're watching the lesson over and over again and you're still not understanding what I'm trying to tell you, it's probably because there's something very basic that I've already covered that you're not comfortable with. Because let me tell you, I'm assuming you know absolutely nothing about chemistry. I'm trying to break it down into the very easy bite-sized chunks. But if you don't understand what a compound is, or a reaction, or molarity, or concentration, or any of that stuff, then there's no way you're going to proceed. So make sure you're comfortable with that. Okay, so we've talked about reactions, we've talked about solutions. In these lessons, this one and the ones forthcoming, we're going to be zooming in great detail on reactions that happen in what we call aqueous solutions. First of all, aqueous solution is a fancy word. It just means water solution. Think aqua, right? Aqua, aqueous. That's all that means. And you might say, well, why do we care about reactions that happen in aqueous solutions, in water solutions? It's because that is where a lot of chemistry actually happens in real life. Think about your body, for instance. Your body is mostly water by mass, percentage-wise. Your blood is mostly water. Lots of the fluids in your body are mostly water. If you cut open your skin, it's very moist. I mean, that's all water. So our biology is basically evolved to be doing the chemical reactions necessary to make energy and waste products and all that stuff all of those reactions are happening in what we call aqueous solutions, which just means solutions of water. So chemistry on Earth, in living bodies like ours, are happening in aqueous solutions. Of course, in the ocean, there's lots of chemical reactions going on in water because our planet's mostly water. So reactions that happen in water, it's not just some side branch of chemistry we're going to talk about. It's essentially important to understanding chemistry because most interesting reactions are happening in water all around us, right? So that's why we're going to zoom in a little bit in detail in these forthcoming sections on what happens in aqueous solutions. And I'm going to warn you right now, this section, this one here, is mostly going to be definitions. And I hate doing a section on just definitions, but if I gloss over them, then you're not going to understand the following material. It's just going to make things harder. So what we're going to do is define some terms. I'll try to explain in great detail exactly what they are so that there's absolutely no confusion. And when we get to the actual chemical calculations, there won't be a big deal because you'll understand what I'm talking about. Okay, first of all, this section is called Electrical Properties of Aqueous Solutions. Electrical properties. You might say electrical, that doesn't have anything to do with chemistry. Well, it kind of does when you think about it. We talked about ions before, right? Which are sort of like charged elements. When we take an electron away or we add an electron to an element, it has a charge. And when you put some of that stuff in water, you have these charges floating around in water, and so you kind of have to start talking a little, at least a little bit about electricity because you have electric charges flowing around, and that's what we're going to talk about here. Let me tell you something that probably 50% of the people watching this know, and 50% of the people do not know. If you take pure water, and I don't mean water out of your tap, that's not pure water. I'm talking about pure water with nothing in it. No salt in it, no chlorine in it, nothing. It's just H2O, that's it. If you purify it absolutely, and you stick 2 wires in that water and hook it up to a battery, there will be no electricity flowing through that water. Water does not conduct electric current. I'll say that again because, like I said, about half the people watching this don't realize this. Water does not conduct electric current. That goes totally against what we're all taught, right? Be careful in the bathroom. Don't drop things in the tub, you know, that have electricity, you know, batteries or whatever, because it's dangerous. It can kill you. It can electrocute you. That is true. But in those situations, in the bathtub or in the swimming pool or even in the lake, that's not pure water. That's water with stuff dissolved in it, right? So let me give you another example. If we take table salt in a glass of water and we put that salt in the water and we mix it around with a spoon, salt's going to dissolve, right? We see that every day. And then we do the same experiment. We stick 2 wires in the water and hook it up to a battery and measure it. Electric current will flow through that water, right? So this is something that's not in dispute. It's fact. Pure water does not conduct electricity, but if you start dissolving things like salt into pure water, it begins to then conduct electricity. So when we are telling you, be careful in the bathtub, don't drop a toaster in the bathtub, well, if you're in the tub, I mean, you have salt on your body and it's sweat, right? It's going to dissolve in the water. The water itself coming out of the tap is not pure. It's got all kinds of stuff dissolved in it that can conduct electricity. So yes, bathtub water, very dangerous for electricity. Standing out in the rain, very dangerous because that's not pure, right? So those things have, that water has stuff dissolved in it, right? So we need to talk a little bit about what happens when you dissolve, let's just, for an example, take salt, table salt, sodium chloride. What happens when you dissolve it into water? Why does that then allow it to conduct electricity? And what we're going to see is that that salt is breaking down into these ions in the solution, and the ions that are then in the solution, the charged atoms, so to speak, is what is then allowing the electricity to conduct. And so these fundamental things we're talking about here, we're going to be carrying through the next several sections as we talk about chemical reactions in aqueous solutions, because it's all going to be talking about what is dissolved in solution and what's floating around, what can react. And so it's all stemming from here when we talk about these simple ideas. So finally, we get to draw something on the board. What if we just have pure water, right? So I'll draw me a little, container like this. It's just a cylinder or something like that. And, just to be cute, I'll pretend that my water is purple. So here's my water, and H2O. And I'm going to say this is pure, H2O. Then basically I'm going to say does not conduct electricity. kind of weird when you think about it, because we're always taught, be careful about water. But if there's nothing dissolved in here, then the only thing you have in here are these water molecules, H2O. And those things are bound up, they're electrically neutral, these molecules that are in there. And if you take a battery and hook an electric current through it, well, first of all, what is electric current, by the way? It's a flow of electrons, right? They have to be moving. So you have to have some medium to conduct the electrons, right? In a wire, there's lots of electrons available. If you look in the wire, because metal in a wire has tons of electrons on the outer layers of the atoms that can then jump around and move around. So if I hook a battery up to a wire, I've got tons of electrons that can just move freely through the wire because there's so many free electrons basically that are sitting around ready to go. But if I then hook this wire up to this water, electrons try to go into the liquid, but there are no charges in here. There's nothing in there to carry. The electrons just can't zoom through the water. I mean, they have to be conducted by something so they can then move freely, or some kind of charge can move freely through the water, but there is no charges that are floating around in pure water, so it can't conduct anything. All right, so let's contrast that situation with a new container. I'll draw this one a little bigger, but still the basic idea. It's just basically a glass of water. And I'll go ahead and say, okay, there's my water. Now the difference, let's say, is I sprinkle some table salt in the top. It goes in and hits the water, and we all know what happens. It dissolves, right? So let's say here I have sodium chloride, NaCl. This is my crude attempt to tell you that's a sodium chloride unit. I'm trying to draw them touching because, remember, this is an ionic compound, right? Ionic compound means something from the left-hand side of the periodic table combining with something on the right-hand side, and it's kind of this lattice, this grid of kind of crystalline, and it's all bound together in this sort of like this lattice structure. That's called ionic compounds. And we talked about all this before in previous lessons, right? So they drop in here, and they're kind of, they're kind of bound together like we're showing sort of here. Once they get into the solution, then what ends up happening basically when they dissolve is the sodium and the chlorine break apart. The sodium and the chlorine break apart, and they're not gone. When you see things disappear, right? You put salt in the water, it disappears. They don't really disappear. What happens is the bonds are basically broken between the sodium and the chlorine, and it happens to millions and billions and billions of these little units of sodium chloride all over the place, and so they break down. And so what happens is the sodium is still in the water, the chlorine is still in the water, but they've all broken down and they sort of fit between the water molecules such that you don't see those granules of salt anymore. They're still there. The sodium and the chlorine is still there. The same number of moles that go in is equal to what the number of moles of sodium and chlorine are going to be in solution. The only difference is you can't see them because they kind of fit between the water molecules and they all break apart, so you can't see them anymore, but they're still there, right? We all know that. We taste the water, it tastes salty, right? So when you drop the sodium in there, and the sodium chloride in there, then what you're going to have is you're going to have Na, which is a positive ion. You're going to have chlorine, which is a negative ion. You're going to have sodium, which is a positive ion, and chlorine, which is a negative ion. Of course, this is just a simple drawing with sort of two of these salt formula units right here. But what's really going on is when you drop them in there, this is billions and billions of these things happening. So there's many, many, many positive sodium ions, many, many, many negative chlorine ions. By the way, how do we know sodium's positive and chlorine's negative? We get that from the periodic table. If you look at the periodic table, sodium, you can look at the column and you can see the charge that sodium is going to want to have is +1. The charge that chlorine is going to have is -1. We've learned all this before when we talked about the periodic table. So if that's not familiar to you, then definitely go back and make sure you understand. Sodium's going to be positive, chlorine's going to be negative. Now, if we take an electric battery circuit or something and hook it up here, the electrons are going to go in. Now we have tons of charges, positive and negative charges, in this solution that can freely move around because they're in water solution. So the electric current can then go through the water back into the other side and back into the battery because we have those charges in solution, all right? So that's why when we dissolve things in water, right, when we dissolve something like salt in water that breaks up into positive and negative ions is what we're calling them, that's when they can conduct electricity. That's why they can conduct electricity. So we simply say, and this is an important word, we say that NaCl dissociates. Dissociates means sort of to break down, all right? It dissociates into sodium ions and chlorine ions. Ion should not be an unfamiliar term. That just means we have an atom, like a chlorine atom has an extra electron on the end. The sodium atom has lost an electron. So it wants to be positive, it wants to be negative. Anything that's charged like that we call an ion. And these ions are what's allowed to move around solution, so when you put the circuit and hook it up to the salt water, it can conduct electricity. All right, that's a long-winded way of basically saying, hey, when you put salt water and hook a battery up to it, it can conduct electricity. If you can remove all of the salt and all the impurities, nothing's going to happen as far as the conduction of electricity. So we've talked a little bit about ions. We've talked about the fact that we have a negative ion in this solution and a positive ion in this solution. We've also introduced a very important word called dissociate. When you read that in your chemistry book, you're going to see this word a lot when you start talking about solution. Dissociate, dissociate. It just means to dissolve into the ions, basically. It breaks down into the fundamental ions. That's basically the dissolving process. That's what dissociation means. It's just another word for that. You know, a lot of chemistry is dealing with understanding what they're talking about. So make sure you understand this one. Now, let me expand on this ion idea a little bit more. An ion is a charged object. In this case, you know, they're atoms and such. For this case, I'll put object in solution. In the context of chemistry, when we talk about ions, we're talking about things that are charged, usually in a solution. Now, there's actually two kinds of ions that we care about, and we actually have them on the board, positive ion and negative ion, right? But we have special names in chemistry for everything, so I'm going to make sure you understand this. We have the anion, anion if you want to call it that way, I call it the anion, and this is the negatively charged ion. And I'm going to change colors to green, and I'll say it's chlorine in this example. In other words, we've been dissolving sodium chloride in solution, so for this particular example, the anion is the negatively charged ion. So that's going to be chlorine. And it has a charge of -1 because we don't write the 1, but when you just have a negative sign, it implies there's a 1. If you see a -2 or a -3, then it means it has a charge of -2 or -3. So that's anion. The other kind of ion, the positive ion, is called the cation ion. Okay? And it is the positive charged ion. And I'll switch colors to have it all on the sheet on the board here. And in this example, it is the sodium ion here. All right, so you really need to take a few minutes to remember this, because what's going to happen in your book when you're reading about things is you're going to see them talk about the anions here. The anions are doing this, they're doing that, the anions, the anions. And then another reaction, they're going to be talking about the cations are important because the cations are talking to the anions. And you need to know what they're talking about. Anion means negative. So you need to say that a million times until you remember it. Cation is positive. If you're a cat lover, cats are positive, okay? I don't know, maybe that doesn't help you, but cats are positive. For some reason, to me, anion seems to mean anti to me, like the word anti, right? So anti is sort of negative to me, anion, anti, you know, I don't know, antisocial, something like that. So anion just means negative to me. It always has, but however is easy for you to remember that the anions are the negative ions, the cations are the positive ions. That is something you need to remember. Now, I want to introduce a few other terms. Some of you guys and girls drink sports drinks, right? So maybe Powerade or Gatorade or something like that. And they always talk about they're full of electrolytes, right? Electrolytes are your friend. When you're working out, you've got to have your electrolytes. They're so important, right? In the context of chemistry, when you see something talking about an electrolyte, it just means an electrolyte is something that when you try to dissolve it in water, it is able to break down like this and dissociate into these ions, right? To dissociate, to break down into these ions. If it's a strong electrolyte, it means that it breaks down completely into these charges. Every teaspoon of salt you put in there totally breaks down into these strong electrolytes, right? And then you have your weak electrolytes that certain substances, when you put them into water, they kind of dissolve. They don't really dissolve that great, and they don't break down that great into these charges. So those are kind of the weak electrolytes, right? And then you have non-electrolytes that basically don't break down at all. So when you see these terms, you need to understand what they are. So let me quickly write them down. You have strong electrolyte. By the way, I'll tell you really quickly, the reason these sports drinks, right, tell you that you need your electrolytes is because, your entire body's chemistry is functioning in a water solution. Your blood, all the chemistry is happening in solution. So when you exercise and such, you're using up all this, basically your body's chemistry is really going, producing that energy, and you're using that energy. So whenever you get thirsty or you need to, quench your thirst, so to speak, because you've been using and exercising so much and using all that energy, supposedly the sports drinks put some of these ions, these electrolytes back into your system that you've been basically depleting. That's why they're so important, right? So it needs your electrolytes. I don't know, scientifically if they really work, but they do taste great whenever you've been exercising, right? So a strong electrolyte is a solute. Don't forget, a solute just means something that we're trying to dissolve, that when put into solution, it exists almost completely as ions. And of course, because of that, it's a good conductor. When I say good conductor, I mean a good electrical conductor. So a strong electrolyte is a solute. A solute is sugar, or a solute is salt, or a solute is sodium hydroxide, or a solute is anything in a teaspoon you're trying to dump into water. Solute is what you're trying to dissolve, okay? So a strong electrolyte is a substance, a solute, that when you put it into a solution, into water, it exists almost completely as ions. That means it completely breaks down. When you take salt and you put a teaspoon of salt in water, it almost completely goes into solution, completely dissolves, completely breaks down into these constituent ions. That's a very strong electrolyte because it completely dissociates like that. All right, and of course we have the weak electrolytes. And by the way, because the strong electrolyte completely dissociates, that makes it a great conductor. There's tons of ions in solution, and the more ions you have in solution, the easier electricity is going to flow. So the weak one, you might guess, is a solute that only partially dissolves in solution or dissociates in solution. Okay, almost only partially dissociates solution, so it's a poor electrical conductor. There's always going to be the guys in the middle, right? These guys appear like sodium chloride. They completely dissolve, they completely dissociate into ions, so they're great conductors. These are the strong electrolytes. The key thing is, it not only does it dissolve, but it breaks into these ions to make them great conductors in solution. Weak electrolytes, or the step down from there, they sort of dissociate, maybe not all of them, but maybe a certain percentage of whatever you pour into the liquid actually dissociates into ions. So because not too much of it actually dissociates, then you have sort of a weak electrical conductor or a poor electrical conductor. Maybe it conducts a little bit, but not really that great because not that much of it dissociates. In other words, it doesn't all want to fall apart when you stick it in solution. And then you have what we call, you might guess, non-electrolytes. And this is a solute that exists almost completely as molecules. and I'm going to put in parentheses, no dissociation. So no breakdown, in other words. So just to state the obvious, doesn't conduct electricity. Okay, so that's why we call it non-electrolyte, right? So you have the three classes, and I could have just told you verbally, but they're pretty important because you're going to be probably tested on at least some of these ideas. So you have the strong electrolytes that dissolve in solution. Not only do they dissolve, they break apart, they dissociate into these ions. So they're great conductors. And then you have a weak electrolyte that they sort of dissolve, but maybe only a certain fraction of it dissolves, and then when they dissolve, you know, it goes into breaking down into the ions, dissociation, but not all of the stuff does, so it doesn't conduct electricity that great. And then you have the non-electrolytes that when you put them in solution, either they really don't dissolve or they don't break down into these ions so much so that they don't conduct electricity, but one way or another you stick it in the water and basically it doesn't conduct electricity. That's the definition of a non-electrolyte. So I want to give you a few examples of what would be, and typically what would be good strong electrolytes and what would be a good weak electrolytes and non-electrolytes, just so you have an idea. So in general, just so you can kind of get a feel, in general, ionic compounds are pretty much always going to be strong electrolytes. So an example is the one we've been using, sodium chloride, right? It's table salt, it's ionic. Sodium is from the left hand of the periodic table, chlorine is from the right hand of the periodic table. It doesn't really exist as a molecule. We've talked about all this before. Sodium chloride is not really a discrete molecule that floats around. It's kind of in a lattice of billions and billions of sodium and chlorine atoms that kind of join as sort of like a lattice structure. And they're ionic in that sense. So we've talked about those definitions before. So most ionic compounds, when you have something on the left-hand side of the table combining with something on the right-hand side of the table, they're forming these ionic compounds. They're almost always going to break down easily in water. And not only are they going to dissolve in the water, they're going to break down into these ions that are then going to conduct electricity really well, so they become strong electrolytes. That's sort of the fundamental thing about a strong electrolyte. It has to conduct electricity well. So let me change colors really quick. Okay, only a few molecular compounds, and I'm going to say mostly acids, are strong electrolytes. And the best example of that would be hydrochloric acid. We've heard of hydrochloric acid. This is also stomach acid. It's what's in your stomach that breaks down food. This is a molecule. Hydrochloric acid's a molecule, and it is one of the molecules that if you put it in water, it dissociates into hydrogen ions, H+, and chlorine ions, Cl negative sign, right? So they dissociate into those ions, and that can then conduct electricity. So if you have a bottle of hydrochloric acid, it's going to conduct electricity pretty well. However, I'm trying to convey to you that it's kind of in the minority, because what we're trying to say is few molecular compounds are strong electrolytes. Mostly some of these acids that we're going to talk about in the next few sections. The best example is hydrochloric acid. Most of these molecular compounds I'm going to write down in a second don't dissociate very well at all, and so they don't conduct electricity. So when you, in general, if you look in, because these are the two broadest classes of things we know about, the ionic compounds and the molecular compounds, right? Most of the ionic compounds are going to conduct electricity great in solution, totally dissociate. And not very many of these molecular compounds are going to do that. The main exception is going to be these acids, like hydrochloric acid. So try to file that away in your mind somewhere. Now, the third thing I'm going to write down is most molecular compounds and organic compounds they are going to be called non-electrolytes or weak electrolytes. Okay, so the best example of this one, and I'll just put it in, and I'll just keep it in red. The best example of this is sugar. Regular old table sugar, right? So what we're saying here is kind of an extension of what we talked about up here. Most molecular compounds don't dissociate very well in solution, and so they don't conduct electricity very well in solution. The main exception to that is what we talked about up here, so the acids like hydrochloric acid, hydrofluoric acid, things like that we'll talk about a little bit later. But most molecular compounds and organic compounds, which organic compounds are molecular, they're bound as molecules, right? They don't really dissolve very well in water, or if they do dissolve in water, they don't totally break down into their ions, so they don't conduct electricity. Best example is sugar. So this is a fantastic solution, really, because sugar and salt basically look the same. I mean, they taste different, but they look the same. They're both powdery crystal substances, more or less, okay? Well, if you dissolve salt in water, we've already talked what happens. The sodium and the chlorine, they break apart, and so you have all these ions floating around solution, so it conducts electricity. If you take sugar cube and put it in water, it's going to dissolve in the water. It's going to disappear before your very eyes, right? So you might think, well, it's going to be a great conductor of electricity. But it's not quite the same thing, because sugar is a very complex molecule. It's not this ionic bond that's going on here. That's a sugar molecule that's very tightly bound. When you put it in the water, it doesn't want to break apart. The reason it disappears is because it's in a crystal. And so when you put it in water, the molecules can separate, float apart, and kind of get between the water molecules, so you don't see it anymore. But the sugar molecules themselves don't actually break down. Right? Here, the sodium chloride's breaking apart into ions. The sugar doesn't do that. It's a very tightly bound, stable molecule, so it stays intact. So what you have in the sugar case is a bunch of water and a bunch of sugar, but the sugar molecules, they don't have any charge. They're tightly bound, they're neutral, they're molecules. So they're all floating around, sugar inside the water, but none of them are charged. So you can't conduct electricity with sugar dissolved in water, right? Only when you have things break down. That's what this dissociation term means. When it dissociates, it doesn't just mean it dissolves, it means it breaks down into these ions. So it's very important that you understand the difference. It's not just that it dissolves in water. I'm giving you a great example. If you put sugar water on the counter and try to conduct electricity through it, it's not going to really do much. The sugar doesn't dissociate. It doesn't break down into any kind of ions. So the three main classes is you have the ionic compounds, which is a huge class of compounds we've talked about. Very strong electrolytes are almost always going to break down in water into ions, so they conduct electricity. The weak electrolytes, I should say the molecular compounds, in contrast to the ionic ones, most of these guys are going to be non-electrolytes, which means they don't conduct electricity, or very weak electrolytes, which means they don't conduct electricity very well, because they don't break apart into these ions. Best example is sugar for the molecular or organic compounds. Now, there are some exceptions. One of the biggest class of molecular compounds that is a strong electrolyte is actually these acids. So when we do reactions with acids very soon in the next couple of sections, the acids are going to be in aqueous solution, right? Just like in your stomach, it's hydrochloric acid in aqueous solution right here in your stomach, right? So whenever things go in there, it can react in solution, and that's because you have the hydrogen, the hydrochloric acid can break down into these ions, so they're free to react very easily in solution. Now, the final thing I'm going to say before closing this section off is a lot of times when we talk about things in aqueous solution, like up to this point, we've written things like NaCl parentheses aqueous solution, right? This would mean salt dissolved in water. We've also used things like NaCl solid. This means the solid powder form, right? So we've used these parentheses to kind of denote like what we're talking about. Here's a solid, here it is when we're dissolved in aqueous solution. This is fine. This is sort of fine to, especially this is what I'm mostly zooming in on in aqueous solution. This is fine to say that sodium chloride is dissolved in aqueous solution. But another way to sort of write it more completely would be to say NaCl as a solid when you put it into water, that's when I put the water on top of the arrow, I mean, you take this, you put it into water, what happens? Well, what happens is it breaks down into Na plus aqueous solution plus Cl minus aqueous solution. This is not really a chemical reaction. I mean, there's no real combining with anything else going on, but it's written like a chemical reaction to show you explicitly what happens. If you take a solid sodium chloride, you put it in water, it breaks down into sodium ions and chlorine ions in aqueous solution. This is exactly what we've been drawing on the board, but it's just kind of formulating it sort of like in chemistry terms so you can kind of see what's happening. Because as we do more chemical reactions in solution, we're going to find that writing it like this, NaCl aqueous, isn't that helpful, but when writing it out in terms of the actual ions that are present in the solution is going to be really useful later on. So we're going to kind of get you warmed up to this the way it's written here so that you're not freaked out by that later when we show you that, hey, this is, when we put it in solution, it's really this. Don't get too scared by it. All it means is you have some sodium in the solution and some chlorine in the solution. They're not atoms though, they're ions. There's a charge on this guy and a charge on this guy, and they're going to be basically floating around the water, free to interact with whatever else we put in that water, you know, if a chemical reaction is going to come about. So that is basically all I wanted to cover in this section. A good introduction to aqueous solutions with a little more detail than we've talked about before. Aqueous solution just means water solution, and that's how most of the chemistry in our body is going on. Lots of interesting chemistry is going on in aqueous solution, so that's why we're going to spend a lot of time talking about it. Whenever we take something and we put it, a substance, and we put it in water, then one of three things is going to happen. Either the substance is going to completely dissociate and break down, in which it's going to be a great conductor of electricity because you have these ions floating around. We call that a strong electrolyte. Or it's going to just break down a little bit, not so well. We're going to call that a weak electrolyte. Or it's not going to break down at all, like sugar. Even though it dissolves, it doesn't actually break into ions. And that's going to be called a non-electrolyte. So those are the three main classes. So we tried to kind of give you an overview of what those definitions are and what they mean. And we've also tried to tell you sort of like in general what's going to break down, what's not going to break down. You should know ionic compounds are going to break down. Molecular compounds mostly are not going to break down, except unless it's an acid. Speaking of acids, in the next few sections we're going to talk in great length about different kinds of acids and how they're going to react with other substances, which are some of the most common chemical reactions that we can study. So follow me on to the next section so that we can continue to build our skills when it comes to aqueous solutions, and so that we can tackle acid-base reactions and oxidation and reduction reactions, which are all coming in the next several sections ahead.